All right, so here we have a sphere, and the first question is to find the center and the radius of the given sphere, and the second question is somewhat tricky. So we need to show that this sphere and the ellipsoid are tangent to each other at a given point, right? So now the first question, the first part is probably going to be okay, so this should be doable. So this should be okay. But the second part is somewhat tricky. So let me first explain how we can even approach the second part, because I don't think that I explained something like this in the lecture, right? So the idea here is to figure out to link material from the lecture to this question, right? So to be tangent to each other, right? So the material in the lecture is the equation of the tangent plane, right? So, and well, basically, if the tangent plane is the same, then, um, well, if the tangent plane to these two surfaces is the same, then basically, we will solve part B, right? So in part B, the the trick is to show that these two surfaces, so the first is the sphere, and the second surface is this ellipsoid, they have the same tangent plane. Well, but it is doable, so you can certainly do it. But if you just rush doing your calculations, then you will end up doing a little bit of extra work, right? So you can do it, but you can do it. You can save on calculation if you kind of understand some little things. So let me explain what I mean. So instead of uh, proceeding and finding the tangent plane directly, so what you can do is, without really finding the tangent plane, you can um, I don't know, understand the geometry behind it, and it is probably easier to understand such geometry for the two-dimensional analog, right? So in 2D, so suppose that you have two level curves. So one level curve is something like f of x, y equals c, and there's going to be another level curve. Sorry, another level curve that has a common tangent line with the first level curve, and the second level curve is going to be g of x, y equals some other constant d. Right now, under which condition do these two curves have the same tangent line? Well, at the same time, you know that the gradient vector is perpendicular to the tangent line, right? So the gradient vector to the first level curve is probably something like this, and to the second level curve is probably something like this, right? But the point here is that in order for this to happen, these two gradient vectors should be parallel to each other, right? So nebula f at a given point, so the point that the common point, let's say, is going to be p0, at p0 should be parallel to nebula g of p0, right? So, and if you compute this, it is relatively straightforward to check if two vectors are parallel, because two vectors are parallel if and only if they are proportional to each other, right? So generally speaking, if you have one vector and you have some other vector, so how do you check that they are parallel, right? So if this vector is something like AB and this vector is something like CD, then to check that they are parallel, basically what you can do, you can I don't know, just directly find, so C over A should be the same as D over B, or if A or C are um, zeros, then you can also find the determinant of the matrix made out of these two vectors. So AD minus BC should be 0, right? So this is the check that two vectors are parallel. But my point being is that you don't really need to write down the full equation um, of the tangent plane here. Yeah, I mean, and of course, in 3D, the idea is the same, right? So what we really need to do, so this is the explanation in 2D because it's just easier to visualize. But in 3D, really the situation is the same, right? So what we really need to check in part B is that the um, two vectors are parallel, right? So if this is f of x, y, z, and this is g of x, y, z. So what we really need to check is that nabla f at a given point. So this is my given point at P should be parallel, sorry, not, it shouldn't be equal, it should be parallel. So it should be parallel to nabla g of P. And so this is what we really need to do in part B. Okay, so let's do it. So let's do this calculation. So let me do part A first. So part A. Okay, so in part A, you know what? Let me maybe switch to the next to the clean slide. So the equation in part A looks like this. So x squared. I'm going to rearrange the terms a little bit. So minus 8x plus y squared minus 6y plus z squared minus 8z plus 24 is 0. Now, how do I mean, why did I rearrange it and how do I see a sphere, right? Uh, the equation of a sphere looks like this. So x minus something squared plus y minus something squared plus z minus something squared equals r squared, right? So now basically I have this part here and minus 8x. What I need to do, I need to complete the square, right? So I know that minus 8x is really the same thing. So let me do it. So minus 8x is really the same thing as minus 2 times 4x. So which means that if I add 4 square and subtract 4 square, then this expression is going to be x minus 4 squared, right? Okay, so let me do it for all the terms. Well, 4 squared is 16, so let me just write 16 here, plus 16 minus 16. So here, half of 6 is 3, so I'm going to write 3 squared, which is 9, minus 9. And this is 8 again, so plus 16 minus 16, plus 24. Okay, so now this part is really x minus 4 squared. Now this part is really y minus 3 squared, and this part is z minus 4 squared. Okay, and besides we have these terms that are still unaccounted for. So minus 16 minus 9 minus 16 plus 24 is minus 17. So these three terms are minus 17. So moving this minus 17 to the right hand side, I get 17. Right? And notice that in the equation of a sphere, the right hand side should be the square of something. So it should be square root of 17 squared. Right? So which means that the answer to the first part is that the center of the sphere is 4, 3, 4. This is the center of the sphere. And the radius is square root of 17. So this is the answer to part A. Okay, now part B is somewhat harder. So, but as I said, to solve part B, I need to, I mean, it is conceptually hard. It's not really very difficult to do, but it is kind of conceptually harder. To solve part B, we kind of need to figure out what to do, right? So let me do part B here. All right, so in part B, I have two, um, two functions essentially. So this is going to be my f, and this is going to be my g, and I need to check that the gradient of f is parallel to the gradient of g. And so yeah, I'm doing part B now. So this is what I'm doing. So part A is done. Okay, we need to show that the sphere, well, just as a sanity check, strictly speaking, we are given that the point 112 is on both the sphere and the ellipsoid, but just to check. So just to check, is it true that it is both on the sphere and the ellipsoid? So substituting it to the equation of the sphere, we get 1 plus 1 plus 2 squared 4 minus 8 minus 6 minus 8 times 2 is 16 plus 24, and this is indeed 0. For the ellipsoid, 3 plus 2 plus z squared 4, 2 squared is 4 equals 9. Okay, check. So the given point satisfies both equations. So it is indeed on both surfaces, on both the ellipsoid and the sphere, right? So what we need to do is we just need to find nebula f and nebula g at the given point, right? So at the given point. So x is 1, y is 1, and z is 2. So partial derivative of f with respect to x is 2x minus 8. Plugging in the given values, we get 2 times 1 minus 8 minus 6. Partial derivative of y is 2y minus 6. Since y is 1, we get minus 4. And fz is what is 2z minus 8. And we know that z is 2, so 2 times 2 is 4, minus 8 is negative 4. All right, so nebula f at the given point is this vector minus 6 minus 6 minus 6 minus 4 minus 4. Now nebula g, gx. Now I'm differentiating g, so I'm differentiating the ellipsoid. The equation of the ellipsoid is 6x. X is 1, so this is 6. Gy is 4y, and y is 1, so this is 4. And gz is 2z, and z is 2, so this is 4. Okay, so this is nebula g. And we see that, well, essentially, nebula g is obtained from nebula f by multiplying with the content. So it is minus 1 times nebula f. So which means that they are parallel, and therefore they do have common tangent plane.